our next speaker who's going to keep us interested, because if we have anything to do with something which will keep us awake, it is money. So let's look at the payment workflows in Ruby with Harman. He's from Chandigarh, and he's been working for over a decade and is still passionate about Ruby. So Harman, over to you.
Thank you. Am I audible? All right, so the last session raised the bar very much for me, keeping people energized. Okay, so I am Harman Sohanpal. I am a solutions architect at Tarka Labs. I have been doing coding for close to 10 years now, and building multiple products from 0 to 1 and then scaling those products. We at Tarka Labs, we use technology to solve our clients' problems, and mostly complex problems whenever possible. So today I'll be talking about one of the problems we recently solved, which was a payment workflow problem. We used Ruby, we used ClickHouse, which is an analytical database. I'll tell you how we reached that stage. And just to set the agenda, I'll start with the problem statement, and then share what the current architecture or the old architecture was. Move on to the learnings we got, how we processed from the old architecture to the new architecture, and in the end we'll look at the impact what it did. So just to set some context, taking example of, let's say, an e-commerce platform, where there are buyers and there are sellers. So the whole idea is that the sellers want to sell their products over to buyers, but they don't have a direct contact. So let's say there comes an aggregator in between who says that, give me all the products. I have multiple partners who are affiliated with me, and they can sell your products and I'll pay you back the money. Now, once the products are sold, so the partners will come in, they'll say, okay, this is the bulk payment. Whatever you want to pay users for, whoever owned this product, you pay them and just tell them what you have paid them for, right? So this is one slide where I will slow down a little. So just want to set the context right, that we are more interested on the whole payments piece, where we are getting the bulk payment from the aggregators and then paying back the sellers. And looking at the architecture, what we had was, we were getting data in plain, simple CSV format. That was the input data. We were using MariaDB for doing all this transactional stuff. There was a store procedure which was running things in series. It was kind of doing the job pretty well. Then the users were getting paid. We had a Rails API where the user dashboard was connected. And as the user dashboard, the users were mostly interested in seeing the aggregated reports, or just getting a CSV dump of things. Depends on how big your reports are. So it was working pretty well. Now, the thing is that why am I here? Then I could just finish my slide right now. So this solution worked pretty well for close to 10 years, but when the scale was low. So the whole problem started happening when we reached the scale. So the current scale that we were working at was, the total records we had was close to 15 billion. And every week we were adding 200 million records and then paying out 500,000 users. So this is where things started getting a little tricky, because the store procedure was working in series, the transactions started slowing down because the data in the table was huge. And then the aggregated reporting using MariaDB, if you are a high-profile user, you would not want to come to a dashboard because we'll just show the loading sign and nothing else. So as a solution, what we thought was, so initially, getting rid of this whole store procedure, we said, okay, let's just go with parallel execution, right? And then we'll have optimal usage of whatever resources we have. Then we wanted our jobs, whatever we have, to be resilient. They should be able to recover if anything goes wrong or if anything happens. They should be able to recover. Then we tried doing optimizations on whatever the bottlenecks were or the weak links were. We looked at how to handle the bulk DB transactions, and once the users were paid at the end, we started rethinking on the whole reporting database. Now, when someone talks about parallel execution, Mahesh has already talked about threads, fibers, and rectors, but this is first thing which comes to our mind, right? Coming in a RubyConf, right? Okay, let's use Sidekiq, right? So I'm aware, I hope everyone is aware of what Sidekiq does, right? It just helps you do background processes. So the first task at hand was, dividing work equally. So even if you have Sidekiq, but we still need to tell, okay, which worker does what and all this stuff. So the first option was, let's say, we have 200 million records, create a worker for each record, right? Which is pretty much doable. But the thing is that the number of workers become unmanageable after a certain point of time, right? You have 200 million workers, and most of the records were belonging to same set of users. So instead of having, this was not a very good idea. The second option could have been like, what, let's create a worker for each seller, right? Still, you have like close to 500,000 workers. But the problem is that there's no even distribution of work. So if you're talking of a real-time application, it's not that every worker is doing, let's say, a particular job. A certain set of workers could be like high-paying users. They could be getting a lot, and then other lot more users maybe not getting a lot of money, right? Then the third piece was, okay, let's not create many workers. We'll keep the number of workers to less. Let's just divide workers randomly. Now, the problem again with this was that, again, uneven distribution of data. We still might get into a situation where, we have like the topmost users in a single batch and all the others used in one different batches, which will still not work pretty well. So how we solved this was, we said, okay, let's just divide batches based on how the work has to be done. So if there's one user who has, let's say, 500,000 records to be processed, right? And there are another, let's say, 100 users who have the same set of records. Why not create multiple batches, right? One batch with just that one user, let them do whatever they want to, and then the other batch could have more users. But then we got into a situation of highly uneven distribution. So I remember one time we got into a situation where there were like 100,000 users in a single batch and 2 users in one batch, right? And that started breaking our transactions. So we put an upper limit on, let's say we have 5,000 workers in one batch. And based on that, we started dividing workers in batches, and this is how we created our batches. And then, the batches data was stored in Redis for faster access. And this is just like a basic code of, how we were adding process into Redis and then batches with states. So I'll talk a little about why state was important, but batches were just, we gave it a UUID, and that's what we were using. So now, once the batches are created, right, the work gets divided into Sidekiq workers, and we have done optimal usage of resources. Now, the next step comes as this, right? So we always feel that, we were talking about test cases in the previous application talk as well. We say, okay, my code has 100% test coverage. I've tested it thoroughly. It will never fail, right? So when you're working in a production app, this is like one thing we should not take for granted, right? Things can fail. Right, so I was talking to a talk by someone, like the person who developed Aadhaar. He was like, okay, what? We had everything sorted, everything was tested, everything. The system caught fire, like literally it caught fire, right? And things can go wrong. So in our case, we are working with money. So if anything goes wrong at any point of time, we'll pay the users twice, right? So idempotency is one important thing for to make sure that if you execute the same worker over and over multiple times, it should still lead to the same set of results. Now, even if you have idempotent workers, so just imagine the situation, you're running a 1-kilometer race, and if I tell you that if any time you fall in between, you have to start from the very beginning. Now, what's the worst nightmare which can happen? You just fell right before the finish line. Now you have to start from the very beginning, right? And then coming from the knowledge of video games, we used to play these big games where we used to have these memory cards where you can save your thing in memory card and say, okay, I want to restart from my last save. Now, when you do this, this is how you can divide your work into chunks and say, okay, I'll do one chunk which is small enough that it's not that even if I fail, I can restart from where I left. So this is what we got into. We were doing work in batches. So instead of having a one full workflow, we said, okay, let's just divide work into smaller chunks. And this also makes sure that, one is that multiple people can work on it, actually, right? Because these are all independent modules. And the other is testing this becomes easy because you're testing one small piece at a time and not everything together. So if anything fails for the first part, you know that in the first case, you'll have to start from the very beginning. But in the second case, you know that workflow 1 has been done for all the batches, right? So then you say, okay, let's just start from the second workflow and not worry about the other stuff. Sorry. However, in the second case, we still failed at the very end. And the difference is that in the first case, we failed when the workflow 1 was complete and workflow 2 started, but in the second case, we failed in between. And by the way, workers can fail at any point of time, even if it is not your problem. So how did we make the workers idempotent? So work was divided, we divided work to run in batches. Then each batch had a state, right? So if anything goes wrong before even starting a batch, we would look at that state and say, okay, has this worker run or not, right? In case the worker has run, in case it's not run, we'll run it again. In case it's already run, we'll move over to the next worker. But then what if the worker fails halfway? One option could be you have everything done within that DB transaction. Right? But that was not possible because we had, like, let's say, even if you have 5,000 users in a single batch, you're doing a lot of transactions. You don't want your transactions also to become big. The second option we thought of was, we have these 200 million or whatever records. We'll create a Boolean in the database saying, okay, if it is done or not done. But then we started getting into DB race conditions because we were reading and writing on the same table. So that is where we introduced the concept of temporary tables. So we said, okay, for each user, we'll maintain what all has been done. So we divided work in batches, so user will have, being processed in batches. But even for each batch, we said, okay, let's just see what state is the user in that particular batch. Now, once we did that, if a worker restarts from beginning, we know what to do. But if a worker restarts midway, still you can figure out, okay, what's the state of the batch? What's the state of user of that batch? And then make sure that all the transactions for the user are happening, in one transaction, so that you know that all the batch has processed or all the users in the batches have processed. Now, what next? Right? We have divided work into smaller chunks. We have things into batches. Now, someone will come and say that, it's not fast enough, make it faster. And as a consultant, we have heard this a lot of times where people will come and say, my API is slow. Can you upgrade Rails to a certain version and then it will work fast, right? Or, the problem is that they don't find out what exactly is the bottleneck, right? So we have a dev, she'll start working on a particular workflow. Now, the point is, have you looked at whether this is the bottleneck, right? People talk about a lot, okay, Rails is slow, move over from Rails to Go or something else, but what if your DB is a bottleneck? What if this is the case? The workflow 3 is the one causing issues, but you're solving the workflow 2. So this was one basic stuff that we did. So the whole idea here was we wanted to get data from SQL, put it into batches of 50,000, and then send it over to S3. So the 3 steps happening was, one was fetching data from SQL, we were converting it into CSV and saving it in a local file, and then copying over the file to S3, right? Do you see anything wrong with this code? Okay, so the problem here was that this whole CSV piece was kind of not required. It had an I/O operation, so what we did was we just converted this small piece, and instead of saving a file into your local and then doing something, we said, okay, let's just get data directly. We were doing it in 50,000, so it was not a big data, which could be loaded into memory, and we uploaded directly into S3, and we saved 3 seconds. Right? So 3 seconds doesn't sound very good, right, when you're working and you're saving 3 seconds. But when you're working at a scale, even 3 seconds can cause a lot of difference, right? So 3 seconds ended up saving this much time, and even if you are running 16 parallel workers, we still ended up saving a lot of time. And then if you're working at a scale, working with like big data, even a smaller optimization can help you improve your overall timing a lot. So the next option was that we have done all these optimizations, the work is happening in batches. So the next option was that how do you handle bulk DB transactions? We were doing transactions, let's say, even if you have to copy over 200 million records from one table to other, so how do you do that, right? So every time we were doing any operation within a batch or anything, first of all, we tried to avoid using these huge production tables. Any update was not done on the table which had 15 billion records. We divided everything into smaller temporary tables, and everything was done in that, right? And whenever we had to read data, the data was read in bulk, and this is more of like also the n+1 query issue. And then updating and inserting data, we're also using the new Rails insert all, upsert all. So this is how the code looked like. You'll fetch everything and then find in batches or something, which was mentioned earlier as well. So you fetch everything and do insert all. Now, the one caveat is that it will not do the validations, right? Let's say you have model validations, but that was handled something outside of this whole operation. And then even if you have to do, let's say, read everything, and then do an update on a certain record, let's say on the amount, you'll do upsert all. And this also we were doing in batches of 1,000, so that it should not be that you're doing a 200 million upsert at the very same time, but doing upserts in a certain batch so that you can have the maximum speed possible. So till this time, we said that the users have been paid. Now what's the next step? A user will come back, say, okay, you know what, you paid me, let's say $100,000. Give me the bifurcation, like what product was sold, where was it sold, when was it sold. I want a bifurcation of by month or by country, by category. So then was another concept, right? So I think if you guys have worked with database, you would know what a normalized database is, right? So, and this is like a basic query, how it looks like for a normalized database. You have sales, you have products, you have categories, countries. And to get like the country name, to get the product name and anything, you have to do a join. Now, in simple words, it looks okay to have joins, but our sales table was huge. So when we wanted to do any kind of joins, the query would never return. Right? We tried adding indexes as well, but it didn't work that well. So the first step we did was, instead of doing reporting on this, why not create a denormalized database? Now, one thing which would happen is you have to convert the normalized data over to denormalized, but this really helps when you're doing a reporting database or a reporting kind of a work. This really helps to optimize on your queries. So even after we moved it over to a denormalized database, the aggregations and advanced searching was still not working very well with MariaDB. Okay, so first option was, let's just get rid of MariaDB and bring something else, but we still required a transactional database because we were doing payment transactions, so we could not just get rid of MariaDB at all, right, completely. So then the other option was, let's use MariaDB for all these transactions and what we are doing, but let's add a new analytical database, right? So the things we looked at was, it should have a faster bulk, right? Because we were doing things in bulk. It should be able to provide you a faster read capabilities. It should have this good aggregations, filtering. And it should have a self-managed low-cost solution, because this was something we were giving to the user. So we cannot expect a user to say, okay, you will come twice a month or twice a week on my website. If you start coming 20 times a week or a month, then my cost become 10 times. So these were a few options that we looked at. Right? Snowflake and Redshift were pretty good with all these bulk writes and the reads and aggregations and everything, but they were pretty costly for us, right? And doing these things for a user-facing thing became a bit of a challenge. ScyllaDB was kind of a Cassandra-based solution, but it didn't have that good aggregation. The reads and writes were good, but the aggregations were not that good. So ClickHouse was one thing which Click does. So one is we were able to host it. So we just had an EC2 instance. We hosted ClickHouse, and that worked pretty well for us. And the things which worked well with ClickHouse were that the user aggregation queries become very fast. Right? So if you're doing the aggregation, you want the amount they have earned in a particular country, and with good indexes, the queries become tremendously fast. It had a good support for bulk inserts. So what we had, and this was the example I showed you, we were dividing data into chunks of 50,000. So we had like everything set over into S3 in a CSV format within a folder, and we just had to get like the wildcard star.csv, and everything in that will get inserted. And inserts work pretty fast, actually, right? And a 200 million kind of inserts we were able to do in 15 minutes, actually. And this was one major thing that we got, was the reporting for the user. So it had a direct S3 support. You can just give that this is the path where I want to upload my file, and give a query saying, select user ID and whatever from where the seller ID is this. You can give other, where clauses as well. But this uploads data directly over to S3, and you can give a pre-signed URL. You don't even have to get the user over to the backend, because otherwise with MariaDB, you would stream the data, get it over to Rails, and then stream it back to the user. But in this case, you can just directly have a pre-signed URL given to the user, and they can download their report. So this is how our new architecture looked like. We were still getting data as CSV format, MariaDB was still involved. The users were getting paid in small idempotent workers, and then we brought in S3. So S3 started acting as a backup of our ClickHouse data as well, where we kept it in S3 for some time and then moved it over to Glacier for lower cost. But from MariaDB, we were converting everything into CSVs, adding those CSVs into ClickHouse, and then we used Ruby ODBC to connect the Rails thing to ClickHouse. And then the user dashboard was not even going to MariaDB. So the writes were happening in a different table, the read was happening from a different table, which kind of worked pretty well. And if we look at the impact, in the older architecture, we started getting into a situation where it was taking days to process all this stuff because everything was happening in series, things would fail. We won't know how it failed or where it failed. But in the new situation, we were actually able to do everything, like converting it to denormalized and everything in a span of 3 hours. And one thing which we liked really about this whole Sidekiq thing was that you can get to know what is happening at what point of time. You get this beautiful dashboard from Sidekiq so that you know, okay, what worker is running, where did the worker go, it's in a dead queue. And given the number of workers were low, we were never getting into a situation where the dead queue is overflowing as well. So as far as the reporting goes, we were taking a lot of time when we were directly from MariaDB, but we ended up getting around 2.5 GB of reporting over to S3 within a span of 9 seconds. And the other problem with this older architecture was, given we were working with the main tables, no temporary tables were involved, the process would slow down after a certain scale. So we had a sweet spot of around 5 billion records. Once you cross that stage, things will slow down tremendously, and you have to archive the table, and that was the only option left with us. But with the new architecture, we were actually working with temporary tables at all point of time. We took advantage of Redis and Sidekiq batches and everything. So the scale had no impact on the process timing. And this used to be our, the user state who used to use our old architecture. And yeah, this is the state of our new user, and I'm hoping I did some justice to the audience as well, because after the whole energizing session, this is where we are, and that's all I had for my talk. And in case we have time, sir.
Let's see if you have any questions. Yes, we do. If you all had not raised your hand, by the way, I would have said he's actually going to give some payment for asking questions. But now that you're lucky,
my bad luck.
Weird.
So my name is Ashutosh Gupta. I was asking, why did you choose Amazon S3? I mean, there are other storage services available too. Why Amazon S3?
It had a good integration with ClickHouse. That was one option. And we were already heavily dependent on AWS, so we tried to use S3.
Okay, thanks.
Do you have any other alternatives? What is working better than S3?
So there's a DigitalOcean Spaces. It works well.
Is it faster?
Yes,
cheaper?
it is faster. Oh. It is faster.
Okay, sure.
Thank you.
Yeah.
I have a question. You are pushing the data from MariaDB in CSV to S3 and then pushing it to ClickHouse. Why you can't directly push it to ClickHouse? Why do you need this intermediary step?
We didn't find something like a Matillion job or something with a direct integration with ClickHouse. So that's what we explored. So the initial plan was we wanted to get it out directly. But given that our stuff was happening on a weekly basis, so it was okay even to do it manually as well.
Instead of storing it as a CSV file, couldn't you have saved it to MongoDB or something?
MongoDB, we had to add an aggregation engine on top of that. ClickHouse supported the direct thing. So are you saying from MongoDB use ClickHouse?
Yeah, exactly.
We could have done that, but I don't see a valid use case around that, because there were two pieces we had to manage. Right now we are not managing CSV. It's kind of acting as a backup for us, and then after a certain point of time, we don't even need that data, right? So it's also always for a worst case perspective. So we are, after I think a period of 60 days, we moved over to Glacier, which is very low cost solution, right? With MongoDB, we have to keep managing that data in ClickHouse and also in MongoDB, which are two different databases.
Okay.
We have one more question here, Anuja.
Hello, my name is Anuj Mohotkar. You said that you achieved idempotency because you were having those issues.
Sure.
So did you build in-house solution for that, or like use some kind
For
of
what?
To like get idempotency?
Idempotency, right?
Yeah.
So this is what I showed, right? So see, idempotency is more of you need to figure out what all has the worker already done, right? So let's say if you do a deployment or something happens in between, your worker fails at that point of time. You get a 30-second, the kill comes up. Your worker fails. Now half of the process is done, half of it is not done. If you know the previous half, what half is already done, then you don't really need a solution to do that, right? See, the solution will also manage, okay, what is already done. You have to tell the solution as well. We just use temporary tables to do the same thing.
Okay, thanks.
Okay,
Still
thanks
have
a
one
lot.
more minute.
Is there one more question? No. Thank you so much, Harman.
I think there's.
There is. Sorry, my bad.
Since you mentioned that you have self-hosted the ClickHouse, right? What sort of resilient mechanism that you have, guardrails sort of thing, to map it with this managed services that AWS and all provide, right? In case of failure, failover, ClickHouse, what sort of resilient reconciliation mechanism that you have built?
Okay, so what kind of failure we're talking about? Let's say the data didn't get added over.
Data didn't get added,
Okay.
maybe like, since you have hosted in EC2, if it goes down, is there any replica mechanism?
Okay, so one thing we had was we always had a backup in S3. Right? That's for a worst case scenario, right?
case.
But even before that, before the workflow ends, we had a validation layer. So that validation layer will look at whether the data has been copied over, has the data reached wherever it is supposed to reach. Now, if it hasn't happened, we have still the data sitting there in our temporary tables, which we can again do that. So this whole validation layer helps us to make sure that we don't lose data at any point of time. So we only delete that whole temporary tables once we know for sure that everything is completed, and everything is done. But we do not have anything like a backup for ClickHouse as such, right? But we still have, like, as I mentioned, the worst case scenarios, CSVs are there or data is there in Glacier, which doesn't have like a very real-time availability. But in the worst case scenarios, we can still get back the data.
Okay, what you're saying is the whole ClickHouse data there is a replica in S3, is what you're saying. All your historical
See,
data
we
is in
are
S3.
using the CSVs to get data over to ClickHouse, right? And we don't delete those CSVs, we just delete the temporary tables we had in MariaDB. Right?
Okay, now I'm not looking at anyone for questions, but you catch Harman around. Thank you so much, Harman. A loud round of applause, please.
Thanks a lot.